Hi, we are the team of MaevelSplendor, and we implemented 3 algorithms for this assignment. The first one is the A-star algorithm. The A-star algorithm is a heuristic search algorithm, and it is quite simple to implement. We mainly use this algorithm for us to get familiar with the game rules as well as the major APIs in it. The trickier part of this algorithm can be the heuristic design, and we decide to implement using a quite straightforward way, only considering the state that our agent is currently in, not taking into consideration of opponent actions and the structure of all the cards on the board, on the deck. So we use a linear combination of score, gem, reservation card, and the card distance to guide us during the search. And this is the implementation of the heuristic design. And actually, surprisingly, it can outperform a lot of agents by using this simple heuristic.
Our second algorithm is Monte Carlo tree search. Our design resembles the original Monte Carlo tree search in every way, except that our white nodes are the states where our agent is making an action, and the black nodes are the states where our opponent is making an action. Our actions are deterministic. We can decide which action to take, but we don't know how will our opponent react. 2 challenges are experienced. The first one is there are too many nodes to respond. The second one is simulation can be very time consuming. We have 3 solutions. The first one is tree pruning. We try to ignore some unnecessary nodes. We decide which nodes to respond with the heuristic. The second one is we use A-star to simulate our simulations. A-star simulation may perform better than the random simulation. The third solution is to set a depth limit. So in our expansion, we can only expand 1 layer, and in our simulation, we can only simulate 1 turn. That means 1 action from our agent and 1 action from the enemy's agent. As to the performance, we managed to defeat Sub Super and Sub Top in the test runs, but we cannot defeat Sub Basic for some weird reason.
The last algorithm we implemented is linear code learning. The main challenge is that the actions varies from state to state, which makes it impossible to have a fixed weight vector to perform update. Also, features are very hard to identify. The last challenge is that our agent could only perform better against the one we have been trained on.
Improvements adopted are that first, we categorize action into 3 categories: collect, buy, and reserve. For each type of action, there's a weight vector, and we can express the feature by computing a lot of information at the state. For example, when buying a card, there are features that measure the benefit it gives us and our enemy for future buying by comparing all cards on card. In this case, we can consider not only for our benefit but also for our enemies. There are also features that indicate the reserve history and noble visits. However, this algorithm might overfit due to the lack of inputs. To solve this problem, we use self-playing. During training process, when going to enemy state, we simulate their potential action by computing Q function based on our own weight, so we can expand more random combinations of state and actions. We also add features to compute a final goal of F3 card to make the algorithm more directed. So it will target on our F3 card from the beginning of the game intelligently, which also enables more noble visits. The following screenshots shows that our agent is quite competitive against a lot of enemies. Even though the linear model has limits, linear Q-learning still proves its success by its great effectiveness and strong readability.
So that's our presentation. Thanks for your listening.